next speaker is Jeremy Gauthier from Guelph University. And he's going to talk about a method I think is really neat, but using SSFP-CRAFT for rapidly pulsed quantitative NMR in trace analysis of PFAS, and that's the environmental part, in the environmental samples. So, Jeremy, take it away.
All right, thank you. Many thanks to Krish for inviting me back again this year to talk about SSFP and PFAS and NMR. It's all my favorite topics. I wish I could be there in person, but it overlaps our final exam schedule, unfortunately. However, I'm still excited to tell you a little bit about what we're doing in my lab with regards to measuring PFAS in the environment. So if you're not familiar with PFAS yet, this is your time to get familiar. It's a pretty ubiquitous environmental contaminant. It's primarily what we're interested in are these heavily fluorinated small molecule surfactant compounds. And it turns out that fluorine NMR in particular is exceptionally useful at measuring PFAS in a whole variety of samples. If you think about the capabilities of NMR and fluorine NMR, one of the nice things is that almost all the fluorine that's out there in the environment is anthropogenically derived. So that means that any time there's a chemical shift that shows up in the fluorine spectra, it's generally of environmental interest. We've seen a lot of talks today with carbon NMR and beautiful proton NMR and soils and more environmental samples. And sort of one of the issues, if you think about doing environmental analysis in complex matrices, is you're not able to resolve individual compounds. Because fluorine NMR, all you're looking for is fluorine, and you have a really wide chemical shift dispersion, there is no complex background, even in things like human serum or soils or biosolids or wastewaters. You can put, all kinds of these samples in the NMR, and you'll just see the anthropogenic fluorine. So it's really powerful. And from the analytical environmental perspective, we don't really care about what types of fluorinated compounds are in the sample. And this is a big limitation in non-targeted mass spectrometry methods, where you need almost to know what you're looking for or know the types of compounds you're looking for. Otherwise, you have a big potential to miss things that don't ionize or that fragment in the ionization source. And if you don't have a labeled reference standard, it becomes very tricky to get really confirmatory analysis by mass spectrometry. So I've been working on fluorine NMR for PFAS analysis for about 7 or 8 years now. And I've analyzed a whole host of samples, things like human serum, agricultural crops, produce off the grocery store shelf, wastewater, influent and effluent, drinking waters, biosolids, even really complex and difficult to get samples like polar bear liver and Arctic fox and Arctic seal. And the thing that's been consistent across all these samples is they all have reasonably high levels of this small molecule trifluoroacetic acid. If you're an organic chemist, it might be one of your favorite solvents to use. If you do separation science, it might be one of your favorite additives to use. As an environmental PFAS chemist, the fact that it exists in almost every single sample to date is very highly concerning. There's a number of reasons why it's so prevalent, but ultimately it's the most common ultra-short chain fluorinated acid out there. And what do I mean by ultra-short chain? If you think about the C8, the thing that everybody's really concerned about when you think of nonstick pans or Teflon cookware or Gore-Tex waterproof materials or grease-proof food packaging, these long fluorinated surfactants are often bioaccumulative. They're very persistent. They don't break down. The ultra-short chain counterparts are very short, less than 4 carbons in length, generally. They're very, very persistent, but they're a lot more mobile in the environment. They're very water soluble. They can reach drinking water systems very quickly. They're very difficult to remove from drinking water. Even if you have a filter designed to capture PFAS, it may not be effectively capturing all the TFA present in the drinking water. So they're very interesting compounds chemically, and they're very prevalent. A large proportion of them come from fluorinated refrigerant gases. If you had your air conditioner serviced or you had a fridge, particularly commercial fridges that are serviced, it's usually filled with R134A, which is also HFC 134A, or the HFO 1234YF. These are two fluorinated refrigerant gases used in refrigeration loops that are replacement compounds because they don't deplete the ozone layer. And the CF bond absorbs a lot of infrared radiation. So these two in particular are designed to break down in the atmosphere to lower their global warming potential. The trade-off of doing this chemistry to maintain the ozone layer and not increase our rate of global warming is almost 100% conversion of at least one of them into TFA, which gets rained out all around the world. So much so that we're pretty confident that rainwater TFA concentrations are quite elevated from 0.2 to 0.7 micrograms per liter. And if it's in the rainwater, it can migrate to the drinking water. So there's a big concern about TFA in the environment. But for a long time, scientists and environmental chemists sort of believe that because it's so short, because it's so water soluble, it should be really readily excreted from humans. So it shouldn't be toxic because it's not going to bioaccumulate within people. And if we excrete it, it doesn't have time to induce a toxic effect. So it shouldn't, but it does seem to bioaccumulate. And if you look at recent human serum testing, again, almost every sample has really high levels of TFA, and the levels of TFA people are finding, they can often be more concentrated than the long chain bioaccumulative PFAS that everybody in the media is very scared by. And so TFA, we're finding it more and more often in people at very high concentrations. And because of this and many other reasons, there's a big interest in the analytical environmental community in being able to accurately measure TFA in a whole bunch of samples. I took this article from a recent publication that looked at TFA and basically the changes when we phased out the chlorofluorocarbons into the F gases. And what you're seeing, as long as you're not red-green colorblind, what you're seeing is that, in the red bars, post Montreal Protocol ruling out CFCs in 2010, the levels of TFA increase in almost every single sample tested. Things like surface waters, things like plants and animals, things like soils and biosolids and produce. So there's a big interest right now in being able to measure these ultra short chain fluorinated acids, because if we can measure them more accurately, we better understand how they're moving throughout the environment. Most people will use mass spectrometry to do this, which is fine. It works okay. There are a few key issues. One is that if you're doing liquid chromatography mass spectrometry, there's only one good fragmentation pattern, and it's a really low molecular weight ion that can often get lost in the spectrometer noise. They're also quite difficult to retain in reverse phase chemistry, although there are a number of advances being made recently. A lot of people have tried using GCMS as well, but the issue here is that it does work well, but because it's such an acidic polar compound, you need to derivatize it first into something more volatile. And that in itself adds a complex analytical step that you then have to validate for your method. So it adds complexity that we don't really want. And the other part of the issue is that TFA is not the only ultra short chain we're concerned with. There are others out there that people are just not interested in yet. Things like the difluoro or monofluoroacetic acid that we know are in the atmosphere. Things like the perfluoromethane sulfonate, carboxylic acid equivalent in terms of the PFAS world. So there's a whole host of these ultra short chain fluorinated acids out there in the environment that we'd really like to measure really accurately. And as it turns out, fluorine NMR might be one of the best tools we have to do this. Fluorine NMR, I mentioned, measures PFAS really well. It measures the ultra short chain PFAS exceptionally well. There's a unique chemical shift for every single ultra short chain compound. And for the most part, like TFA, it doesn't overlap any other PFAS. So if there's a chemical shift there at -76 in methanol, it's 99% likely that will be trifluoroacetic acid. So that in itself makes it quite powerful, in addition to not seeing the background noise, not worrying about solvent peaks, not worrying about is it ionizing in the mass spectrometer? Can we see its transitions? So we don't need to derivatize it. And it really, really works quite well in fluorine NMR. The trade-off always has been, though, sensitivity. This is something that we're really pushing. How low can we actually make our 1D NMR so we're able to see these things in the environment? This is a fluorine NMR spectra just showing some of the ultra-short chain fluorinated acids and in amongst other long chain PFAS. And I'm just showing here that things like TFA or the perfluoromethane sulfonate, they're very easily identifiable in this beautifully clean spectra. This spectrum, by the way, it's an extract of a wastewater treatment plant, and so you're not seeing any of the other lipids or proteins or fatty acids or even water from this sample. All you're seeing is the really nice fluorinated compounds. So last year at IFAN, I talked about our use of the SSFP, the steady state free precession pulse sequence. We see it as the best technique we have at the moment to address the sensitivity limitations when we're dealing with environmental NMR. If you're not familiar with it, the idea is essentially you keep all your nuclei in a steady state of constant decay, such that your time between pulses is on the order of milliseconds. And this allows you to collect thousands to millions of scans in the same experiment time as a few hundred to a few thousand scans in conventional 1D NMR. So it's been exceptionally powerful for pushing detectability of compounds, particularly when it's combined with CRAFT analysis. So I pulled this figure from the paper, and what this is really showing is that on the top in that red spectra is a conventional 1D fluorine NMR, an 8-hour experiment. You see a number of fluorinated things. In the middle is the SSFP result, and that's just 15 minutes of experiment time, and you see all the same fluorinated components plus more. And then on the bottom is the crafted analysis. So what CRAFT does for SSFP is it mitigates a lot of the issues when working with heavily truncated data. So if our time between pulses is only 30 milliseconds, you can imagine that FID becomes heavily, heavily truncated. And then in the 1D NMR spectra, the conventional Fourier transform result, you see all sorts of truncation artifacts and wiggles in the baseline, and any solid component of the probe gets highlighted in SSFP. And CRAFT is able to cut through all that and give us really beautiful spectra with increased detectability of things as well. Right? So we're seeing more things in the sample in much shorter experiment times, which is exactly what we need for environmental NMR at trace concentrations. One of the things we've often done with the SSFP technique, and this is in the supporting information of the original paper for fluorine NMR, is that we optimize the flip angle to avoid saturation of the signals. We're not trying to do a saturation experiment. We want to maximize our signal to noise. And the trade-off with this is that even if you're collecting thousands and thousands of scans, you're really only collecting 5 to 10 degrees of magnetization of those scans. So even if you double or quadruple the amount of scans you're going to collect, you're not necessarily getting twice the signal to noise or a corresponding increase in signal to noise. And this really is highlighted when you look at larger molecules that relax very quickly versus very small fluoride ions that take a long time to relax. You get a correspondingly much greater increase in signal to noise in those molecules or in those nuclei that relax more quickly. And this is something that we showed in the paper as well. And it's simply because as they relax more quickly, you're incorporating more of that decay, more of that magnetization as part of the signal. So the question for me became, what if you just force all the nuclei to fully decay within that 30 millisecond time between pulses? Then you're collecting 90s for thousands and thousands of scans per minute. And not only that, what if we could have 5 times the T1 within that 30 millisecond time between pulses? Then we could have quantitative NMR with a 30 millisecond time between pulses, which gives you, 4,000 scans every 2.5 minutes of fully quantitative 90-degree NMR signal. And it turns out you can do this if you're very careful about the way you approach it. What's the best way to get nuclei to relax in NMR? It's, of course, to use paramagnetic relaxation agents. So what I've done here is develop two parallel NMR experiment methods. One in organic solvents that uses everybody's favorite crack to reduce the relaxation times, and one in aqueous solvents that's using gadolinium chloride or gadopentetic acid, again, to reduce that T1 time, that relaxation time. The reason there's two parallel methods is if you're dealing with environmental samples, oftentimes you'll end up with a methanolic extract. So if you're extracting, a solvent extraction in plants, or if you're doing a solid phase extraction of complex wastewaters, you'll often end up with methanol. And I wanted a method that worked really well for those organic extracts. And I also wanted a method that worked really well for aqueous samples. So we could move towards direct analysis of rainwater or drinking water even. And the nice thing with the aqueous side is the gadolinium tends to work a lot more efficiently at relaxing those nuclei. So there's two parallel methods, but both of them work very well. Now, the one thing you might think of is if I'm adding 16 mg per mil of chromium into my sample, which is the solubility limit of chromium, ACAC, and methanol, what happens to my signal? And in Fourier transform, it disappears really quickly, particularly with the gadolinium chloride. You can see here that with 4 mg per mil, there's no way we can get a peak area to quantify that. Even with 2 mg per mil, it's a little bit iffy. But the really nice thing with CRAFT is that it's able to recover these very broad signals from very, very short FIDs, from fast relaxing compounds. It does this really well. So this is the SSFP-CRAFT result of this same sample with the same relaxation in it. And you can see we are getting signal to noise back. And the other really nice thing that CRAFT can do is it can predict in silico what the FID should look like at 1.2 seconds or 2 seconds. So you're able to retain and recover a lot of that line broadening. Right? And now even at 8 mg per mil of gadolinium chloride in an aqueous sample, you can still quantify, you can still get a peak area. But oftentimes what's better for us as environmental analytical chemists is you can just go into the table of amplitude and frequencies and pull out the data directly without having to look at the spectra anymore. So it's become very, very powerful for this type of work. So we have two parallel methods, one for aqueous samples, one for methanolic samples. The aqueous samples works exceptionally well. The T1 time of TFA, which is one of our smallest molecules, is under 6 milliseconds. That means in a 30 millisecond time between pulses, we can get quantitative NMR. Because chromium is not quite as efficient of a relaxation agent in organic solvents, our time between pulses there is about 200 milliseconds. Still very, very fast, but not quite the same signal-to-noise boost as an aqueous sample. So what does this actually mean then? We have a really nice method. It works really well. What can we do with it? And I'm showing you here the instrument detection limits for TFA in methanol or in D2O or H2O. And this is concentration in the actual NMR tube. And what you're seeing is that, for the methanol, we're doing quite well. But for the aqueous analysis is where the method really starts to shine. We're not yet at the level or at the capability of a tandem mass spectrometer with LCMS, but we've far surpassed the capabilities of GCMS. So in just 45 seconds of experiment time on NMR, we get a lower instrument detection limit than GCMS can do with a 12-minute run. Keeping in mind that GCMS still needs sample derivatization and ideally a mass-labeled internal standard. All of this data was produced on a relatively new Bruker spectrometer, the advanced NEO generation with an iProbe on a 400 megahertz instrument, or a 400 megahertz field strength. We've seen even nicer improvements than this on higher field strengths, of course. But some really nice detection limits. And if you start to pull in the typical concentration of TFA in rainwater, we're now approaching the ability to collect rainwater in an NMR tube and get quantifiable data out of this about real-time TFA concentrations in the environment without touching the sample at all. And this is so incredibly powerful because we're avoiding biasing our sample by extracting it. This, for me, is the ultimate goal of analytical environmental NMR. I want to put the sample right in the spectrometer without touching it because it removes all of this question that we have when we're dealing with detection of unknowns. So the question you may have, and the question I get all the time, especially from the reviewers, is why don't you just run a very fast 1D NMR and get the same thing? Right? Why don't I just set my D1 to 30 milliseconds, my acquisition time to 30 milliseconds, and my D1 to 1 millisecond, and just run it as a standard 1D? Why do we need SSFP? It's because SSFP has a phase incrementation built in, which gives you a uniform response. It avoids Dante type mutations or excitations in the window we're interested in. So, plus or minus 50 ppm from the O1 for the O1P, we get a consistent response allowing for quantitative analysis. Without the SSFP, I have tried it, but you get really substantial nulls and excitations within our window that we're interested in quantifying. So the SSFP here is necessary, and the CRAFT is necessary to make this work so nicely. So what I'd like to do in the last couple of minutes of my talk is just walk you through a couple of examples of things that we're looking at right now with quantitative SSFP NMR. This is a drinking water sample taken from Toronto, Ontario, up here in Canada. It's 500 milliliters of tap water that we've extracted, and you can measure TFA at quite high concentrations for drinking water. What's also showing up is the short chain perfluorinated sulfonate that very few other people are actively looking for. This is a sample of Arctic fox. And what was interesting with this sample, we're not seeing TFA. It's a very small sample, but we are seeing other fluorinated things that we can now quantify. So we're seeing a very high concentration of this aromatic CF3 component that we then use to say to our mass spectrometer, we're looking for this particular structural motif. Are you able to help elucidate what this unknown might be that we found in the NMR? This sample I find a little bit scary in some ways. This is a spinach sample. This is organic spinach taken from a local grocer. There's a lot of PFAS in this sample, but what's really striking to me is the high concentration of TFA that we're finding. And for me, this can particularly point to, or potentially point to, why we're also seeing high concentration of TFA in human serum. Because the food we eat is often heavily contaminated with trifluoroacetic acid, particularly produce, because it collects it from the rainwater, it has nowhere to go, and we end up consuming it. And I hypothesize this is contributing to the elevated levels of TFA in human serum. And that's ignoring all the other PFAS we're seeing in this organic spinach sample from the grocery store. This is, of course, human serum. So it's 1 milliliter of human serum. And the experiment time it's still quite lengthy. It's 6 hours. But this 6 hours incorporates almost 1 million full 90-degree quantitative NMR scans. And we're able to quantify TFA in the human serum, as well as other perfluorinated compounds and fluorinated pharmaceuticals. I believe this is my last example, food contact paper. I was interested in whether or not TFA was going to be found within food contact paper. We didn't see it in this particular sample, but we did see it, and this is a recent sample, a recent coffee cup purchased on campus here. What we did see is there are still very high levels of other types of PFAS that we don't necessarily want next to our hot beverage in a coffee cup. So to put it all together, we're moving towards trace analysis by NMR. This has always been my goal. Can we do direct sample analysis using NMR of very, very low trace amounts of perfluorinated compounds? With the SSFP plus the paramagnetic relaxation agents, and in particular the use of CRAFT to recover those line shapes, we're doing much better than GCMS, and the sample preparation is much, much easier than what you might do for a mass spectrometry workflow. I will point out, if you want to run this, if you have a Bruker spectrometer, you can run it today. Send me an email. I'm happy to help you get started. If somebody wants to rewrite it for VNMRJ, I'm open to that, absolutely. I have a lot of people who would love to run it on their Agilent or their Viridian systems. And I'll point out that you're getting the signal to noise improvement equal to or greater than installing a cryoprobe with no actual investment in your NMR hardware. So it's really, really powerful. And I've tested it across a whole bunch of probe and console configurations, a whole bunch of generations, different types of probes. It's worked very well on all of them. And it's not just fluorine. So I'll sort of point out that these are some nuclei I'm working with at the moment with a bunch of different collaborators or in different areas of chemistry. Proton and carbon, it works well, but also for doing nitrogen-15 studies or phosphorus or even tellurium labeling in biomolecules, we've seen great success using the SSFP-CRAFT with quantitation. So I'll leave with my concluding thoughts. One is that and this is a big one, using fluorine NMR is actively changing the field of PFAS research. We're finding more compounds than ever before. We're seeing more and more people use fluorine NMR to investigate PFAS in environmental samples. So it's actually making a huge difference right now in the field in terms of the amount of things we're finding and building new research questions as well. It's an unbiased method of analysis. It's somewhat non-destructive. Adding the chromium or the gadolinium does make it now a more of a destructive method, but it's still, you can take the sample and use it for something else. But critically, we're not trying to replace other techniques. We're trying to enhance them, adding cross-validation or complementary analysis. And as I said, we're finding new things every day, which is a little bit scary, the amount of PFAS we're finding out there, but it's also really beneficial to furthering our understanding of these global contaminants. So thank you so much for your attention. I'm more than happy to take questions, and thanks again for the invite.
Thank you, Jeremy. Questions? Yeah. Who first? I'll go with Brian first. Oh, yeah.
Thanks, Jeremy. That was a good talk. As far as the instrument configuration, are you using a fluorine optimized probe, or what kind of probe is it?
Yes and no. So in the past, we've run it on a fluorine selective probe, but more recently, I've run it on a TXO probe here at the University of Guelph or one of the newer iProbes at the University of Toronto. So there's really no probe dependence. Some probes have more fluorine background than others, but CRAFT is actually able to tease out the fluorine background probe component from the actual spectrum or from the actual sample.
Okay. Are you using an internal reference of some sort, TFT maybe, or how do you reference?
Yes. So for the organic samples, it's difluorobenzophenone as the internal reference standard. And for the aqueous samples, it's this trifluoromethylbenzoic acid. Both
it's,
of
it's all internal referencing, so you put it in?
Yes, yeah. I have not tried an heretic standard yet, although an external reference would work equally as well.
Question?
Thank you for the talk. Really cool work. And as a NMR spectroscopist, I was always jealous of the GC mass spec. So this is really nice to see. A non-NMR question: why is it that the trifluoroacetic acid is so what's the right word? Persistent. How should we think about this? And I'm thinking the close analogy of that is an acetic acid versus trifluoro. Is it pKa? What makes this different?
Yeah, it's a good question. So I guess trifluoroacetic acid and the whole PFAS family, they're very acidic compounds. So you can imagine you have all that electronegativity from the fluorinated tail pulling on that carboxylic acid functional group. But the other side of the story is there's nothing that can break that CF bond. And so it's what makes them such persistent compounds is that out in the environment, there is to date no that I know of anyway. No microbial pathway, no photolysis mechanisms, no hydrolysis or reductions that can actually break apart that CF bond. The only time we see it breaking is if you heat up these compounds above 700 or 800 degrees Celsius. And then you generate sort of F minus. So I think that's one of the main contributors. The long chain PFAS are very bioaccumulative because they're essentially analogous to fatty acids. But the short chain, I don't want to say they're bioaccumulative because they shouldn't be, but they're very prevalent or very present in human samples. And I think that's just a matter of how much of these things we're actually ingesting on a day-to-day basis is giving very elevated levels in human serum. There's a lot of research still to be done in that area, but that's sort of my personal hypothesis.
Yes. Here.
Hi, Jeremy. Great talk. And yeah, super important since, industry is moving towards these shorter chains to overcome, these bans. So I have a question about, do you see, since you're pulsing so quickly, any sort of sample heating when it comes to this?
Yeah, that's a good question. That's a fair question. Short answer, yes, but not from where you expect. So if you, to give you a little bit more detail, there's a little bit of sample heating depending on your specific install. Older systems that have a greater airflow through the probe tend to have less sample heating. But the sample heating we see is coming from the decoupler. So all these spectra are proton decoupled fluorine, and the decoupler is on basically all the time because you can't really pulse it that quickly. And that is where our heating is coming from. It's about 0.2 watts, depending on the console or depending on the configuration. If you actually do, though, the calculation and say, how many watts per second am I applying to the probe from the fluorine channel, it's about 10% of the power being applied by the decoupler. So we're still sort of well within what I would consider a safety margin in terms of heating the probe. Just with regard to the SSFP, the only heating we see comes from the fact that the decoupler is on all the time.
Thank you.
Okay, if there are no more questions, thank you, Jeremy.
Thank you.